Now let us compute the probability of error. That is, at the receiver end, we would like to compute the probability of making wrong decisions at the receiver end, like the average probability of it. So consider a very simple scenario again, in which we have two signal classes S0 and S1, and as you can see, there is a threshold defined here, gamma naught, which draws the line between the two decision regions. One decision region is for the signal class S1, and the other decision region, the left hand side, is for the signal class S0. So whenever the test statistic, that is variable that you compute at t is equal to capital T, whenever that test statistic falls in this region, left hand side, the blue region, the receiver is going to take decision in favor of the signal class S0. And whenever that test statistic value is greater than this threshold gamma naught, and it will fall in the right hand side region, then the receiver will take the decision in favor of the signal class S1. You can also see the two likelihood probabilities plotted here, and they overlap together in between these two regions. This blue one is for the signal class S0. That is, it is the likelihood probability of the received signal Z given S0 sent, and the red one is a likelihood probability for received signal Z given signal class S1 sent. Now let's see how we can compute the error event out of this scenario, and what are the regions of errors, and how we can see those regions here in this block diagram. Now let us suppose we transmitted the signal class S1 from the transmitter N with the norm A1 mentioned here, and somehow, because of the noise, this norm value changes and goes below this threshold point gamma naught and comes here on the left hand side, somewhere here, right? Now if you see and compare the two PDFs, the likelihood PDFs, the value of the PDF, the red PDF here, the value of the PDF is smaller than the value of the blue PDF there. For all those points below gamma naught, the value of the likelihood probability indicated with red color, which is the likelihood of signal class S1, it is smaller than the likelihood of signal class S0, right? So for all these points below the gamma naught, if the test statistic comes out to be below gamma naught, the receiver is going to take decision in favor of signal class S0. Why? Because we have seen in the map rule, we are taking decisions on the basis of likelihood probabilities, and taking the decisions in the favor of signal class that results in the highest likelihood probability. So here, if the test statistics fall below gamma naught value, gamma naught threshold value, the receiver is going to take decision in favor of signal class S0, because the likelihood probability of S0 within this region from minus infinity till gamma naught is greater than the likelihood probability of signal class S1, right? So you transmitted S1, and because of the noise, your amplitude varied, and it resulted in a smaller value than gamma naught, and it resulted in the left hand side, or the region of signal class S0. Then you took a decision in favor of signal class S0, and that's the error decision that you made at the receiver end. And likewise for signal class S1, suppose you send transmitted signal S0 from the transmitter N, and somehow because of the noise, the value of your signal goes beyond this threshold gamma naught and moves into this region, right? The receiver is going to take decision in favor of signal class S1, because here the likelihood probability of the signal class S1 is higher than the likelihood probability of the signal class S0, right? So these are the error events, and how many such error events you can have. If you see these tails, the blue tail here starting from gamma naught till infinity, and the red tail there starting from minus infinity till gamma naught. These are all those points for which you are going to make errors, right? So if you can somehow integrate them, right? So if you can integrate them, you will get the and take the average of it, you will get the average probability of error out of this scenario, right? And that's exactly how we are going to do. So next slide, we are going to talk about the mathematical derivation of error probability, which is very simple. If you have understood this, it's going to be very simple. We are interested to find out these area under the curves of these tails, right? We would like to accumulate them to find out the average error probability in the given digital communication scenario. Right, so let's consider this simple scenario again, in which we have two signal classes S0 and S1, and let's see how we can compute the probability of error given such a system. Assume that the signal class S1 was sent from the transmitter end, and because of the noise you end up taking decision in favor of signal class S0. So in that case the receiver will record this as an error event, and you can express it mathematically as probability that hypothesis H0 is chosen given the signal class S1 was sent. That is equivalent to probability of error event given signal class S1 sent, which is nothing but the area under the curve of the overlap region starting from minus infinity till gamma naught. This will be your area under the overlap of all such events when you took a decision in favor of signal class S0, whereas you actually sent signal class S1. In all those regions, the probability density function, the likelihood probability of signal class S0 will be greater than the likelihood probability of signal class S1. You can see here the gray portion there. In all those areas and regions, the likelihood probability of signal class S1 is greater than the likelihood probability of signal class S0, right? So you are going to integrate, and we are assuming that this tail goes below this point till minus infinity. So in general you write it like that you integrate it from minus infinity till gamma naught, till this threshold point gamma naught, and you integrate all that area, the shaded portion there, which is nothing but the probability of Z given S1, that is the PDF, the tail PDF of this likelihood probability density function, which is probability of Z given S1. You are integrating the tail of it starting minus infinity till the threshold gamma naught, right? Now let us assume the other way around. Suppose signal class S0 was sent, and at the receiver end you took the decision in favor of signal class S1. That is, you choose hypothesis H1 given signal class S0. Now if you see this figure 2 there, the shaded portion marks all such error events in which the probability likelihood function of received signal given signal class S0 is smaller than the likelihood function of received signal Z given signal class S1. You can see here in the gray portion, the tail of the likelihood, the first likelihood function is having smaller values compared to the likelihood function of signal class S1, right? So the receiver is going to take decision in favor of the signal class S1, whereas actually you sent the signal class S0. So all such events starting from gamma naught till infinity, if you integrate all, if you integrate the PDF, the tail PDF starting from gamma naught till infinity, you are going to accumulate all such error events, right? So that's why the integral here starts from gamma naught till infinity. And what you want to integrate? You are going to integrate the probability of Z given S0. You are integrating the tail of it starting from gamma naught till infinity, right? So the total average error probability is the sum of these two errors events, and they are defined using this formula there. And in general you can use a summation to write it in compact form. That is probability of error given S1 times probability of S1, the number of times that you send that signal, right, that is there, plus probability of error given S0 times the probability of the signal class S0, right? The likelihood of signal class S0. So in short, these two hypotheses are going to get added together given the signal class S1 and signal class S0. Let's see how it reduces into a more simpler form in the next slide. So if we assume that the signals are equally likely, that is, they are equally probable, then the likelihood probabilities, probability of S1 and the probability of S0, the likelihood probabilities of the signal classes S1 and S0 are going to be same, that is 0.5 each. So we substitute 1 by 2 against these two probabilities, right, in this step, and we end up getting these two remaining terms. Now if you see the regions of overlap here, and specifically these shaded portions, these two shaded portions are symmetric in nature. That is, if you compute the area of this tail, this one there, this is going to be exactly equivalent to the area of that tail there, right? So whether you compute both of them independently or you compute either one of them and multiply it with 2, you're going to get the same result, right? So using this symmetry by observing the PDFs and their tails, you simplify this and substitute probability of hypothesis H1 given S0 here in this equation, and reducing it into this form, right? Hence the probability of bit error PB is the probability that an incorrect hypothesis is made, and next we are going to substitute this probability, and it's nothing but the area under the curve of this PDF. Like I said earlier, this is equivalent to integrating the tail probability of Z given S0 starting from gamma naught till infinity. It's repeated here, right? And in the final step, you have to substitute the equation or the expression for this likelihood probability of Z given S0, and it's represented using a Gaussian function. You can see here it's a Gaussian function shifted at the mean A0, and you all know very well what's the equation for the Gaussian function, repeated many times in the past and repeated here as well, right? So all you have to do is to integrate this equation starting from gamma naught till infinity, right? So let's see how we go about it further and see the maths behind it. It's how we simplify it and come up with a very nice form of probability of error. Here we suppose few variables. For example, the argument here in the bracket is assumed to be U equivalent to Z minus A naught divided by sigma naught. So we assume the argument as U, right? And if you substitute in terms of U, you end up getting this equation modified form here. This the limits will also change accordingly, because the limits were previously applied on the variable Z, right? Z was varying from gamma naught till infinity. Now since you have supposed U equivalent to Z minus A naught divided by sigma naught, so the Z will also have another expression, and it comes out to be, using a simple calculus, it comes out to be A1 minus A naught divided by 2 sigma naught till infinity when you integrate in terms of U, right? Now this is a standard expression. This term in box, rectangular box that we have just come up with is a standard representation for the Q function. The Q function is expressed here. If you somehow face such a problem in which you have to integrate an exponential like that, right, under these limits, some finite value till infinity, you can have the tabular form of it using Q function, and this is available and this information is there. You have the tables that can calculate the value of PB, which is the error probability, using the Q functions, right? So what we are doing here in this step, in these two steps, we have simplified our problem of integral in terms of the Q function, right? We couldn't get the closed form using this integral. However, we can get the tabular form using the Q function, and we are given with Q tables that are pre-calculated numerically against different values of the arguments of the Q function. For example, here if you see the argument of Q function is 0, you end up calculating Q of z as 0.5. These values are given, right? So all you have to do is to compute the argument of Q function, which is z. And what is the argument of Q function here? Z is nothing but a1 minus a naught divided by 2 sigma naught, right? So you have to compute this argument in order to get the probability of error, right? So next we see and focus on this argument, what is it, and how meaningful it is, and perhaps we can represent the argument in some meaningful form, right? By the way, this Q function can also be approximated using this exponential function, and this is commonly used in calculating the values of the Q function given the argument x. You can also compute it, you can also approximate it using this formula, right? So let's see how the argument translates itself into some meaningful form, the argument of Q function. If you see here, in the argument you have a1 minus a naught divided by sigma naught. If you compute the squares of it and then take the under root of it, you can express it in this form here, right? And you know that a1 and a naught are nothing but the norms of the signals being plotted on the constellation diagram. a1 and a naught are the norms, right? And norm is nothing but the under root of energies, right? So here we are computing the energy difference between the two signals. If you see here, the norms are being subtracted together and then squared, right? And all that it would be left with is the difference of energy, right, which is expressed with ED. So the argument translates itself in this useful form in which we have substituted the noise variance in naught by 2, and we have expressed the numerator in terms of the energy difference. So if you see the table again here, as the argument increases, the probability of error decreases. You see, the argument is 2.9 here and the probability is very small, 0.001, right? So somehow we need to increase the argument of the Q function if we are to minimize the error probability in our digital communication system. And how to minimize it? If we can somehow increase the energy difference between the two signal classes, the numerator will become higher, and as a result the argument of the Q function will be high. And when you have the high value of argument of a Q function, you end up getting smaller value of probability of error, right? And if the energy difference is small, you end up getting small value of the argument of Q function, and therefore you end up getting high values of probabilities, error probabilities. And also intuitively, it is also intuitively simple to understand. Suppose the energy difference between these two signals is very small. This means these two signals will be very close to each other and the overlap will be very high. And it's highly likely that you are going to make wrong decisions at the receiver end. And whereas if you increase the energy difference between these two signals, right, if you separate them in space, in terms of their energy, right, one signal is placed here and the other one placed there, right? So the PDFs will hardly overlap together, right? The PDFs will hardly overlap together, and therefore the shaded portion as mentioned there against the two possible errors will be very small, right? So it's going to support our intuition as well that as the argument increases, the probability of error reduces, and therefore the energy difference between the two signal classes increases as a result, right? Now let's express this probability of error function further and see how we can make more intuitions out of it, and specifically for the three signal classes that we are going to talk about shortly. One of them is this antipodal signal class, in which those two signals are opposite in nature but having equal energy. And the second one is the orthogonal signal class, in which the two signals are orthogonal to each other, plotted on constellation diagram like this. And lastly, another signal class which we call unipolar signal class, in which one of the signal is 0 and the other signal is having some energy E, right? It's like an on-off signaling. You send something for on period, and then you send nothing when the transmitter is turned off. So we are going to see how we can further compute and further have the probability of error expressions for these three signal classes. For that, we are going to express our ED, which is the energy difference, in terms of the signal terms. For example, ED is nothing but the difference of signal and taking the square of it and then integrating it. It's the energy in the difference value, right? So here we compute the difference of the two signals, S1 of t minus S naught of t, and then squaring it and integrating it as per the energy formula requirement to compute the energy difference ED. If we express this term there, and you can come up with three more terms if you express this formula, right? So the three more terms indicate the computation of energy of signal class S1, the computation of energy of signal class S0, and some value there, right? The product of the two signals along with the integration of it, right? Now let's see further how we can reduce this for the three specific signal classes. Assume for the first case we have antipodal signals, in which capital M is equivalent to 2. Why M is equivalent to 2? Because we have two signals, S0 and S1. The capital M is equivalent to 2, and we have only one basis function to represent it. If you calculate the basis functions for the representation, it will come out to be 1, right? If you have antipodal signals, the basis functions will come out to be 1. So capital M is equivalent to 2, capital N is equivalent to 1, and for antipodal, let's see what's the energy difference that comes out to be. So energy difference will be nothing but 4 times the signal's energy, the symbol's energy. How? This term will give you some value ES. This term will also give you some value ES. And this term again will give you the value ES. Why? Because one of the signal is opposite to that of the other signal, that is S1 of t is equivalent to minus S0 of t. So you substitute one of the signal in terms of the other signal, the negative sign will come in, will disappear, and it will become positive. Suppose you substitute S0 of t equivalent to minus S1 of t, so negative will become positive, and this will become S1 of t square. And if you integrate S1 of t square, it will give you ES again. So you end up getting 4 times ES as a result when you compute it for antipodal signal classes. And now let's see how you substitute the value of ED there in the Q function and have other transformations of it. So the Q function we derived was from equation 3.63 is repeated here, right? So all you do is substitute the value of ED there in the equation, which is 4 times ES, and it will reduce in this form there. The 2 will in the denominator will cancel out with the 4 there. You end up getting this thing. Now I have also talked about the representation of ES in terms of EB, where EB is nothing but the average signal energy per bit. And here we have symbols energy. It could have more than let's say 1 bits in it, but in our example it can only have 1 bit per symbol. Since it's a binary scenario, we can only have 1 bit per symbol. So in our example, ES is basically equivalent to EB. But here EB is the average signal energy per bit. We don't forget about that, it's the average, how much energy on the average is there in per bit, right? So ES is related to EB using this expression. We have talked about it in the class in the first few lectures of this course. ES is equivalent to EB log 2 of M. Here capital M is equivalent to 2, so log 2 of 2 is 1, right? So effectively this is equivalent to 2 times EB, which is repeated here, right? So that's the another representation of our probability of error in terms of average energy per bit, average signal energy per bit, right? So the same we obtain for orthogonal signal class, in which again we have two signals, capital M is equivalent to 2, and we assume the two signals are equally likely in nature and equal energy. So let's see how the ED reduces itself when we assume that we have two orthogonal signals at hand. One of the signal is orthogonal to the other signal, so that's why this product there, which is nothing but the integration of the two orthogonal signals, right, over the period t, this answer will come out to be 0 when you're going to integrate it. So ED will come out to be ES as a result, and if you substitute there, you end up getting this function Q of ES over N naught under root, right? Now again we repeat for the unipolar signal class, in which capital M is equivalent to 2 again, and we assume equally likely signals, right? But here we have a slightly different scenario, which I'm going to shortly explain here. If you compute ED out of the same expression as we did for antipodal and orthogonal, if you express the term ED here again, remember one of the term is 0, because we are not sending anything when the transmitter is turned off, and we are sending some value signal, say S1 of t, when the transmitter is turned off. Since it's unipolar on and off kind of a signal, so you send something for one period, symbol period t, and you send nothing for another, let's say whenever the bit 0 is sent, you send nothing, right? So in effect you are not sending any energy when the transmitter is off. So as a result, the value of ED will come out to be ES. So when you substitute the value of 0 for the second signal in the two expressions there, the ED will come out to be ES, right? So you substitute the ED here equivalent to ES in the Q function, you end up getting this function there, right? Which is the probability BB expressed in terms of the signal energy ES and the noise spectral density and naught. Now since for unipolar scheme we are not transmitting anything at all when bit 0 is sent, therefore we must take this into account into calculations while calculating the error probability in terms of EB. Remember, EB is the average signal energy per bit, but here for one of the bits we are not using any energy, we are not sending any energy, so we have to take this into account, and let's redo some calculations. EB log 2 of M is equivalent to 1 by 2 times 0 when you send binary 0, and 1 by 2 times signal energy, let's say S1 of t, when you send binary 1. What is this 1 by 2? Because we assume that the two signals are equally likely, so half of the times you are sending the signal S0, and half of the times, another half of the times, you are sending the other signal S1 of t, right? For signal S0, you're not sending anything, that is the energy of that signal will be 0, right? But for signal S1, yes, you are sending some energy, and the energy will be computed as per the energy formula, and would be equivalent, it will be equivalent to ES. So as a result, EB log 2 of M, log 2 of M is 1, right, in our example. So EB would be equivalent to 1 by 2 times ES as a result, or in other words, ES will be equivalent to 2 times EB. So if you write ES in terms of EB for unipolar scenario, you would be substituting 2 times EB there, right? And the 2 will cancel out with this 2 there in the denominator, and you end up getting this equation there, right? So what it turned out to be that for the unipolar, the error probability expressed when it is expressed in terms of average energy per bit, it is exactly equivalent to the case of orthogonal signaling when the same is expressed in terms of average signal energy per bit, right? But for unipolar, when you express it in terms of signals energy, symbols energy, right? Then that is different compared to either antipodal or orthogonal, right? Now let's see which of the signal classes, either antipodal, unipolar, or orthogonal, which one of them will give you the lowest probability of error. If you compare the formulas that we have just seen, this one for antipodal and this one for orthogonal, right? And this one for unipolar. Unipolar and orthogonal have the same probability of error, probability of bit error, right? Whereas this formula there for antipodal, it has a different value, right? If you compare these three, the unipolar and the orthogonal are the same. Whereas this one there, antipodal, it will be the lowest of all. Why? See the numerator here, it is 2 times EB, whereas in the unipolar and orthogonal case it is only EB. The numerator, or in other words the argument of the Q function for antipodal is higher than the argument of the Q function for either unipolar or orthogonal. This one is for orthogonal and this one is for unipolar. So when you compute the probability of bit error, the antipodal will give you the lowest of all, right? So that's the conclusion drawn out of it, and I'm sure that you would be also doing the same in the labs and would be comparing the probability of error for various different signal classes, right, against different values of noise and the channel conditions and the energies. You would be computing these probability of errors and would be comparing it with these Q functions. These are theoretical error probabilities given the values of energies and the noise powers. So these are the theoretical error probabilities. You'll be computing your theoretical error probabilities and comparing them with the practical ones that you would be having using MATLAB simulations in the labs, right? And see how far you deviate from these theoretical values. You most likely would be closely following the theoretical curves if you do everything right. Right. So next time, inshallah, we would talk about various examples of probability of error, and we will also come up with some simpler methods of computing the error probabilities. The method that we have seen today is more expressive, and it might be tedious to calculate the error probabilities and follow the series of derivation every time when you compute the error probability. I will also teach you the simpler method or the shortcuts to obtain the Q function very easily and intuitively given the signal classes when they are expressed in the constellation diagram, right? So let's see till next time, and I'm looking forward to receive lots of questions during this during the interactive session that we are going to have for this lecture. See you then.